I keep talking about that shared variability, and the multicollinearity command or variance inflation factor can help us better understand what this shared variability is. So just like with the assumptions, this command for testing multicollinearity is called a post-estimation command. So this will be performed on the previous regression that you fit. And the command here is estat VIF. And that VIF stands for variance inflation factor. And with this output, we get a table that tells us the VIF, or the variance inflation factor, for all of our predictors, and the 1 over VIF. That's simply 1 divided by your variance inflation factor. Now, let's kind of break this up and figure out what this command is actually doing and what these output tells us. So stat is doing a lot behind the scenes that doesn't actually show you. And what it's doing is actually fitting 3 separate regression models, including our independent variables, as the DV. So it's fitting one model regressing research, the DV, onto build and innovative, the 2 IVs. And then our VIF is related to the R squared for that model. Now, if you think about what the R squared for a regression with research as the dependent variable and build and innovative as the independent variable, that R squared is going to tell you the amount of variability in research that can be accounted for by hours spent building and how innovative the project is. So that's just the variability in research that can be accounted for by our other 2 independent variables. And now our VIF is calculated with a pretty simple equation. It's simply 1 over 1 minus R squared. And remember, this R squared comes from the regression, including research as the DV, or build as the DV, or innovative as the DV. In these regressions, our actual dependent variable of judge ratings is not included in the model at all. Now, really the main takeaways you need from this output is that the higher the VIF, the more multicollinearity is an issue. So a VIF of 10 or greater would be would suggest problematic multicollinearity. And that's because you can't really parse apart the variability in research from the variability in your other independent variables. Now we also get this 1 over VIF score, and this is a little bit more practical in its interpretation. Similar to the raw R squared, this is written as a proportion, so you can also interpret it as a percentage. So for the research line, you can convert 0.77 to 77.35%. And now that 1 over VIF kind of tells us the opposite of R squared. While R squared tells us about the variability explained, this tells us about the variability that's free to vary with our independent variable. So for research, this is essentially saying that 77.35% of the variability in research is not accounted for by build or innovative. So this is free variability to predict our outcome. And in this case, the larger the value, the better. So the smaller the value, the more multicollinearity is an issue. And more specifically, 0.1 is a problematic 1 over VIF. And that simply means that when you have less than 10% of the variability that's free to be unique with our outcome variable, then multicollinearity is a really big issue. So VIF less than 10 is appropriate, and 1 over VIF greater than 0.1 is appropriate. Okay. That 1 over VIF is telling us about the variability that's free to predict our outcome, that's unrelated to our other 2 independent variables. Okay. If we consider the 1 over VIF for innovative, 0.90, that's telling us that 90% of the variability in innovation scores is free to vary uniquely with judges' ratings. So while all of our independent variables were correlated with each other, they aren't so correlated that multicollinearity is really an issue when interpreting the regression model. Now, of course, that doesn't mean it's not in that collinearity isn't influencing the betas. We can actually see that our betas are a little bit weaker in the multiple correlation, or sorry, the multiple regression compared to the simple regression, but it's not so problematic when interpreting the regression equation. And the last thing we do before we move on to the assumptions is just fit this equation. So let's write out the full regression equation for this model, including three predictors. So our predicted y will equal the constant coefficient, which is 14.30. I'm just going to be rounding to two decimal places here. Negative 14, sorry. Plus the beta for research times x for research, 0.17 for hours spent building times x build, plus 6.70 for innovation times x for innovation. So this is the full regression equation for this multiple regression model. And this is what we can use to predict future outcome. This is what we can use to predict future judges' ratings. Now let's go ahead and test the assumptions for this multiple regression model. Remember that the assumptions for regression are all about the residuals, or the error in the model. And for this reason, we can't test the assumptions for the model before we fit the model itself. Now, the first thing that I'm going to do is just create a new variable with the actual residual values. Remember, the residual is just the difference in the actual value minus the predicted value based on that regression line. So I'm going to create this new variable with the command predict. I will name it Multiresid. You can name it whatever you want. I decided to name it Multiresid so that I know that this is the residual for the multiple regression. And then the subcommand comma residuals is letting Stata know, predict this new variable based on the residuals from the previous model. When we run the command, we can see we have this new variable here. So let's consider the assumptions of both homoscedasticity and linear relationship between error and predicted value. To test both of these assumptions, all we have to do is interpret the RVF plot, or the residuals versus fitted values plot. The command here is quite simple, RVF plot, and then this y line at 0, that's just letting Stata know to print a straight line at 0. This helps us to visualize the spread of our dots around that y line. Remember that 0 means no error at all. So the closer to 0 a dot falls, the less error that, or the closer it is to the actual regression line or the predicted value. Now, the assumption of homoscedasticity simply means that our data points cluster around that 0 line the same along the fitted values. So there wouldn't be close clustering at one end and wide dispersion at another end. And you really just interpret this visually. We can see here that we have quite a bit of variability on either side of the 0 line along the regression line. So I would say that this is pretty homoscedastic. There isn't any systematic clustering of these dots close or far away from the regression line. And remember, when we're considering homoscedasticity, we're looking for what's called fanning. And fanning simply means that at one end, the dots will be very close to the 0 line, and at the other end, the dots will be very far from the 0 line. Okay, so you might see data points closely fit this type of fanning behavior, but that's not what we see here. So I would conclude that these data are homoscedastic. Now, when considering a linear relationship between our residuals and fitted values, again, this is completely done visually. We just want to confirm that this zero line that we've already drawn is the best fit for these data. So do we have equal number of data points on either side of the zero line all along the regression line? And again, here, I would say we've met this assumption of linearity. It certainly doesn't look like a curved line best fit the data, and that line at zero seems to be appropriate. Now, this RVF plot, or residuals versus fitted values plot, takes into consideration the full model. You weren't asked to do this in your practical, but Rachel did cover it in lecture, how to get an RVP plot, or residuals versus predictor plot. When you do multiple regression, you also want to look at if each of our predictors meets these assumptions. So I encourage you to test this out on your own and look at each of the RVP plots for this multiple regression, just if you want to do that for fun. Okay, and lastly, we're going to confirm normality of our residuals, and there are many different ways that we can look at the normality. The first thing, of course, is just to visualize the spread of our data with a frequency distribution. So histogram, our residual variable, and then I'm defining 8 bins. From this figure, we can see that there certainly is central tendency. There is a clear peak there. And then we do have a lot of data in this lower tail, which would probably suggest a platykurtic distribution. But this end looks just fine. So it looks like at the very beginning of the figure, we're sort of violating the assumption of normality, but it's not so extreme. And we can, of course, confirm that with a Shapiro-Wilk test. Right, so the command here is swilk multiresid. I'm just doing this on our residual variable. Now, remember the Shapiro-Wilk is one of the only statistical tests where we do not want to reject the null hypothesis. Again, I'll say this every week, the null hypothesis for a Shapiro-Wilk is that the data are drawn from a normal distribution. If the p is less than 0.05 and we reject that null hypothesis, we would come to the conclusion that the data are not normal. But here our p-value is greater than 0.05. We fail to reject the null hypothesis and confirm that the residuals are relatively normally distributed. Right, so that all checks out. All of the assumptions of regression have been met. Now there's one last important step.